Everybody, welcome back. We're continuing Chapter 9 with Section 9.9 on altering equilibrium conditions and Le Chatelier's principle. So in an equilibrium reaction, by altering the reaction conditions, you could temporarily favor pushing the reaction towards making more products or making more reactants. And so, for example, we might change the concentration of reactants so that we get more product produced. And this would be called pushing the reaction to the right because we'd favor making more products and it would tip the balance this way. We'd make more products. Or we could alter the conditions so that the reverse reaction was more favored. We'd make more reactants and we'd tip the balance this way. And so this is called pushing the reaction. We can push it to the right to favor products, or we can push it to the left to favor reactants. And what direction we push an equilibrium reaction is going to depend on the reaction conditions. It's going to depend on the concentrations of the reactants and the products. It's going to depend on the temperature. And if gases are involved in the reaction, it's going to depend on the pressure. So we're going to talk about all those three things and how they affect pushing the reaction to temporarily favor making more products or making more reactants. This is really important in chemistry because as chemists, we want to be able to predict and control our chemical reactions so that if we want to make a desirable product, we have the conditions set up to make as much product as possible. Or if we want to slow down a chemical reaction and we don't want to make something, that we can alter the conditions to control the chemical reaction and push it back towards reactants. So Le Chatelier's principle says that if a stress is applied to a system in equilibrium, the system will readjust in the direction that best reduces the stress imposed on the system. So what this means is that if you apply a stress, like you say increase the concentration of reactants, the concentration of reactants goes up, then what the system will do, this is a stress, is the system's going to try to get rid of this stress. It's going to readjust. And how it's going to do that is it's going to favor pushing the reaction to the right. It's going to take these reactants that have been added, the stress, and get rid of it by converting them into products. So in response to increasing the concentration of reactants, you're going to end up producing more products. And this is Le Chatelier's principle in action. If you stress the system, it's going to respond to get rid of the stress. Another thing that could happen, let's say we have reactants in equilibrium with products. Let's say you decrease the concentration of products, decrease concentration. So if you're essentially taking away products, that's a stress to the system. And so what the system will do is it's going to try to adjust to reduce that stress. So if the stress is taking away products, reducing the concentration of products, the system is going to respond by pushing the reaction to the right to make more products. And so the concentration of reactants will go down as the reaction rate to the right picks up and you push the reaction to make more products. So whatever the stress is, whether it's related to concentration or temperature, if you have an exo or an endothermic reaction, or pressure, if you have a reaction involving gases, Le Chatelier's principle says that the system, once that stress is applied, is going to try to readjust to get rid of or reduce the stress. So for example, in this reaction between hydrogen gas and iodine gas, H2 plus I2 makes hydrogen iodide, HI. According to Le Chatelier's principle, if we add more H2 to the system, this is the stress applied, the reaction is going to adjust to minimize the stress and then reestablish equilibrium. So if we added more H2, the rate of the forward reaction is going to increase to reduce the stress of having more H2 added. So if we increase the rate of the forward reaction picks up speed. It's going to use up this excess or added H2 faster to alleviate the stress or get rid of it. So the reaction is going to temporarily favor making more products. And we say that the reaction has been pushed to the right until the stress is reduced. The arrow is favoring making more products. It's being pushed to the right to get rid of this stress, this added H2. And so the concentrations of H2 and I2 are going to decrease because the forward reaction has been sped up. So H2 is being consumed and I2 is being consumed more rapidly in the chemical reaction. So they're going to be used up and their concentrations are going to go down. And the concentration of HI is going to go up until the stress has been minimized, until the added H2 has been used up or reduced, and the system reestablishes equilibrium where the rate of the forward reaction and the rate of the reverse reaction are once again equal. So let's kind of talk through another example. Let's consider this equilibrium mixture in a closed vessel where you have H2O gas plus CO, water plus carbon monoxide, in equilibrium with H2 gas and carbon dioxide gas. So if we added more water, H2O, to the flask, how would the concentration of each reactant and product compare to its original concentration once equilibrium is reestablished? So we add H2O. So this is our stress. We're stressing out the system by pumping in more of this water vapor, water gas. So if this is our stress, the system's going to respond by trying to get rid of the stress. How it's going to do it is it's going to be pushed to the right so that the forward reaction rate increases so that this added H2O is used up in the chemical reaction to make more product. So what's going to happen is the concentration of CO is going to go down because as the forward reaction rate speeds up, CO is being consumed more rapidly than it was before. The concentration of H2O is still going to decrease because it's going to be used up, but because we added more H2O, it's not going to decrease necessarily the same amount as CO, because if we didn't add any carbon monoxide, but we only added H2O, then we have extra H2O to use up, but we don't have any extra CO to use up necessarily. But both of their concentrations are going to decrease because our stress of adding extra H2O is going to push the reaction to the right, so the stress is reduced. When we push the reaction to the right to make more products, the concentration of H2 is going to increase, and the concentration of carbon dioxide, CO2, is also going to increase. So what we want you to be able to do with Le Chatelier's principle is we're going to go through some different conditions that can push reactions to the left or to the right. And we want you to be able to predict what's going to happen to each of the reactants and products. Are their concentrations going to go up or down? Is the reaction rate to the left or to the right going to be sped up? And this is just talking you through kind of that answer for this slide and this concept check. So there's three common stresses that are applied to chemical reactions to alter the equilibrium, to push the reaction to favor products or to favor reactants. We can change the concentrations of the reactants or the products. We can increase or decrease the temperature, and we can increase or decrease the pressure. So these are common stresses that chemists use to push equilibrium systems to the left to make favor reactants, or to the right to favor products. So let's talk about concentration first. So if we add reactant, for example, Le Chatelier's principle says the system's going to shift in the direction that alleviates or reduces that stress. So if we're adding reactant as our stress, the system is going to shift to get rid of that stress. So how it's going to do that is it's going to push the reaction to the right. So we're going to favor the forward reaction, which means that the concentration of O2 is going to go down. Concentration of O2 will decrease, and the concentration of our product, CO2, is going to go up as the reaction is pushed to the right, favoring the forward reaction to get rid of this added stress of adding more reactant. If we add excess product as our stress, it's kind of like the opposite's going to happen. If our stress is adding excess product here, it's going to shift the reaction to the left to favor the reverse, which means that this excess product that was added, CO2, is going to be consumed by the reverse reaction to produce oxygen gas and carbon monoxide gas. It's going to drive the reaction to the left. So our concentration of carbon monoxide is going to go up, and our concentration of O2 is going to go up. Instead of increasing the concentrations of reactant or product, you could decrease the concentration of reactant or product. You could remove a product from the reaction. So let's say we remove H2O that's produced in this reaction. We take ethanol and we convert it into ethene, C2H4, and water. So if we remove the water from the reaction mixture as it's produced, say we filter it or we heat it to get rid of it, we remove it somehow, as we're removing product, this is the stress. And so the system's going to adjust to minimize the stress. So if the stress is removing water, the system's going to try to replace the water that was removed. And so the reaction is going to favor the forward reaction. And we're going to drive or push the reaction to the right to replace the water that was removed. So that means that our concentration of our reactant of ethanol is going to go down because it's being consumed faster. It's being used up to push the reaction to the right. And our concentration of ethene, C2H4, is going to go up because we're favoring the forward reaction to try to make up kind of the stress of removing water from the system. This is actually why precipitation reactions typically go to what we call go to completion. Most precipitation reactions just have a one direction arrow instead of a two direction arrow, because in a precipitation reaction, whatever's turning into the solid is precipitating out a solution. And so it's no longer part of the equilibrium process. Only things that are aqueous or gases are part of the equilibrium expression, because once something precipitates out a solution, forms a solid in solution, the solid is a pure substance and it's not going to participate in this equilibrium reaction. So when you're forming a solid as part of a chemical reaction as one of your products, it's like you're constantly removing product as that solid precipitates out a solution, which is going to drive the reaction to the right, which is why many precipitation reactions, all of them that we've done in this class, feature arrows that just point strictly to the right, because the product is always being removed as it precipitates out of the solution. It's constantly driving this reaction to the right to produce more and more of the products. Okay, so let's talk about changing the temperature and how we can push equilibrium reactions to the left or to the right to favor products or to favor reactants. So the effect of temperature on the equilibrium constant and what direction we're going to push a reaction, what way it's going to favor, depends on if the reaction is exothermic or endothermic. So in endothermic reactions, remember, energy is like a reactant. The reaction needs heat energy to proceed. And in exothermic reactions, heat energy is like a product of the reaction. And so in an endothermic reaction, if we write in heat like it's one of the reactants, we can apply the same principles of Le Chatelier's principle. So if we added heat to the system, we heated up an endothermic reaction, it'd be like adding a reactant, increasing the concentration of heat. That's the stress. And so the system's going to respond by trying to get rid of that stress, and it will push the reaction to the right to make more products. For an endothermic reaction, if we removed heat, it's like decreasing the concentration of one of the reactants. And so the reaction is going to respond by pushing the reaction to the left to replace that heat that was lost. So again, if heat is added to the system, the equilibrium is going to shift to the right to favor making more products. The concentration, therefore, of the reactant is going to decrease because we're shifting, favoring the forward reaction. So we're going to use up, in this example, more of the CO2 to do that. And the concentration of both of the products will increase. We'd expect the equilibrium constant to increase because our concentration of products is increasing as a result of pushing this reaction temporarily to the right. So when the concentration of products is large compared to the concentration of reactants, KEQ is a positive number significantly larger than 1. For an exothermic chemical reaction, heat is like an energy product. So if we pencil in heat here as one of the products as the chemical reaction, we can again apply Le Chatelier's principle. If we add heat to the system, it's like we're increasing the concentration of one of the products. And so if that's our stress, the system's going to respond to try to minimize that stress. So if we added heat to an exothermic reaction, it would try to get rid of the heat. It'd try to convert and do the reverse reaction. If we cooled down an exothermic reaction, we decrease the amount of heat, the reaction would respond to try to minimize the stress. If the stress is getting rid of heat, it's going to try to replace that, and it will favor pushing the reaction to the right to favor making more products. So again, you treat heat as if it's a product in the chemical reaction, and then you apply Le Chatelier's principle to that. So if heat is added to the system, the equilibrium is going to shift to the left to try to get rid of that stress. And if heat is removed from the system, the opposite's going to happen. It's going to shift to the right to try to reduce that stress by replacing the heat that's being taken away. So if heat is added to the system, equilibrium is going to shift to the left to favor the reverse reaction. And so the concentration of the reactant is going to increase and the concentration of the product will decrease. And we could predict that KEQ would end up decreasing because our concentration of reactants would go up as we're favoring the reverse reaction, and our concentration of products would go down. And so you'd have a large number in your denominator here, which results in a decimal value, a small value for KEQ. Our third condition we can alter to shift equilibrium left or right is pressure. So pressure and altering the pressure only has an effect for systems that have gases as a product and as a reactant. If you don't have any gases in your system, changing the pressure isn't going to have an effect on equilibrium. And so something to check for if you get a quiz or an exam question or a homework question involving gases in Le Chatelier's principle, or pressure in Le Chatelier's principle, is to check that your system has gases in it. And so if you increase the pressure in a system that has gases, it's going to cause the system to shift to favor the side with the fewest moles of gas. So in this example, we have carbon monoxide gas reacting with oxygen gas to make carbon dioxide gas. So on the reactant side of the chemical equation, we have 2 moles of CO and 1 mole of oxygen. So we have 3 moles of gas total. And on the product side, we have 2 moles of CO2. And so if you increase the pressure, it's going to shift the system in whatever direction has the fewest moles of gas. So in this case, the products has the fewest moles of gas. So if we increase the pressure, it's going to shift or drive the reaction to the right to favor the forward reaction, making more product. If we decrease the pressure, it's going to drive the reaction the opposite way to the left. If we're decreasing the pressure, it'll have the opposite effect and drive the reaction in the other direction. I always remember this one by remembering that increasing pressure shifts it to the fewest moles of gas. It's like it's trying to, like the side that has more moles of gas, when you increase the pressure, is kind of getting squeezed together more. You're increasing the pressure, so you're decreasing the volume according to Boyle's law. So the side that has more moles of gas, these gas reactants in this case are going to be colliding with each other more often. So their reaction is going to start to happen at a faster rate. versus the side with fewer moles of gas, as you're increasing the pressure, because there's just less gas there, the effect of the pressure is not going to be as great. The effect of increasing the pressure is not going to be as great. It'll still increase the number of collisions, but it's going to increase the number of collisions on the side with the more moles of gas to a greater extent and push the reaction to the side with fewer moles of gas. So pressure is only going to affect equilibrium when gases are involved, and only when the moles of gas on each side of the equation is different. If you have 3 moles of gas on the reactant side and 3 moles of gas on the product side, altering the pressure isn't going to change the equilibrium, pushing it to the left or to the right, because it's going to have an equal effect on both the reactants and the product side. So changing pressure only works if gases are involved and when the moles of gas are different on each side of the equation. So for example, hydrogen plus oxygen to make water, we have 3 moles on the reactant side of gas and 2 moles on the product side. So we check that we have gases involved, and the moles of gas change from 3 to 2 on each side of the equation. So the pressure change will result in a shift in equilibrium. If we either didn't have gases or the moles of gas was the same on both sides of the equation, changing the pressure would have no effect. In this case, it'll have an effect because we have gases and they're different on each side of the equation, the moles of gas. So if the pressure of this system is increased, the equilibrium is going to shift to favor the side that has fewer moles of gas. And in this example, that would be the product side. If the pressure of this system were decreased, the equilibrium would shift to favor the side with more moles of gas, the reactants in this example. Here's another one, hydrogen gas plus chlorine gas to make hydrogen chloride gas. We have gases, so pressure could have an effect on equilibrium, but if we check then the moles of gas on each side, we have 2 moles of gas on the reactant side and we have 2 moles of gas on the product side. So changing the pressure won't have any effect on the equilibrium. It won't cause it to shift to the left or to the right. So you might think, well, could we shift equilibrium by adding a catalyst that speeds up reaction rates? Won't that have an effect on pushing the equilibrium, say, to the right to favor products? The answer to that is actually no. So catalysts won't affect the equilibrium constant KEQ because they're not going to cause a push specifically favoring the left or the right. The catalyst would speed up the reaction in both directions for an equilibrium reaction. So there would be no net effect on the equilibrium. So adding a catalyst won't affect the equilibrium constant. The lower activation that the catalyst provides helps the reaction go forward, and it would also help the reaction go backwards. And so the 2 effects cancel each other out, and it ends up being no net effect if you add a catalyst. So let's do a quick concept check on Le Chatelier's principle. So what factors will affect the equilibrium of a reaction according to Le Chatelier's principle? Concentration, temperature, and addition of a catalyst, temperature, pressure, and a catalyst, concentration, temperature, and pressure, or concentration, pressure, and a catalyst. Well, we just talked about that catalysts don't affect equilibrium. So options A, B, and D can immediately be eliminated. And then if we check option C, concentration, altering the concentrations of reactants or products will affect equilibrium. Temperature will affect equilibrium. And pressure can affect equilibrium, again, if there's gases involved and if the moles of gas is different on the reactants and product side of the equation. So a summary slide for Le Chatelier's principle. When an equilibrium system is stressed by a change in conditions, the equilibrium position is going to shift in the direction that minimizes or reduces the stress. So we have 3 conditions we talked about: concentration, temperature, and pressure. So if we start with concentration to summarize, adding reactants is going to shift the equilibrium to the product side because you want to get rid of the stress of adding extra reactants. So we're going to get rid of that stress by converting the reactants into products and shift the equilibrium to the right to favor making products until equilibrium is reestablished. If we remove a reactant, removing the reactant is the stress. So the equilibrium is going to shift to minimize that stress. And so it's going to want to replace the reactant that was removed. And so equilibrium is going to shift to the reactant side and favor the reverse reaction. It's going to be pushed to the left. If we add product, adding product is the stress. We're going to want to get rid of that stress, is what Le Chatelier's principle says. And so to get rid of that stress, it's going to shift the reaction to the reactant, shift the reaction to the reactant side to get rid of that product that was just added. It's going to favor the reverse reaction. And if you remove a product, it's going to shift the reaction to the product side. Again, that would be the stress is removing the product. And so to minimize or readjust to account for that stress, it's going to want to replace the product that was removed. So it's going to shift the reaction and make more products to favor the forward reaction. We talk about temperature. Increasing the temperature shifts equilibrium to the product side for an endothermic reaction, because heat is like a reactant in an endothermic reaction. So it's like you're increasing the concentration of one of the reactants. And it's going to shift equilibrium to the reactant side for an exothermic reaction, because in an exothermic reaction, you can treat heat like it's a product. If you decrease the temperature, decreasing the temperature shifts equilibrium to the reactant side for an endothermic reaction and to the product side for an exothermic reaction. And pressure, our last one. For pressure to have an effect, you must have a difference in the moles of gas and the reactants on the product side. And if you increase the pressure, it's going to shift equilibrium to the side that has the fewest moles of gas. And if you decrease the pressure, it's going to shift equilibrium to the side that has the greatest moles of gas. So you'll get practice with Le Chatelier's principle in the homework, predicting what direction a reaction is going to be pushed based on changing the conditions of the reaction, changing the concentrations, changing the temperature, or changing the pressure. Please feel free to reach out if you have any questions. This is the end of chapter 9. We'll start chapter 10 next. Thanks, everybody. Bye.